is the way I'm seated right now. Hopefully I can just cut myself out from the green screen and then overlay myself onto the actual text. So hopefully I'm editing this together where it's like I'm floating in front of this document right here, okay? All right, what is up, you guys? It's me, Anthony, obviously. Wow, I can already just like hear my own voice from like the acoustics right here. I live in a 1-bedroom apartment, and this is the 1 bedroom. And I actually do not use it as a bedroom. It's kind of, if you want to think of it, my cat son, it's his bedroom. He sleeps or hangs out in here during the day, during part of the night and stuff, because he will sleep on top of me, or rather he will get up on top of me in order to look out the window to be scanning with his night eye vision for mice in the grass that are like just tens of yards away from my slider door anyways. But I'm doing a little bit of an experiment and recording in here, and so I honestly don't know how the audio is going to turn out. But anyways, I have this green screen behind me, as you can see. And I got this green screen back when I started this channel back in 2017. And I really only used it for the very first video. Well, actually, no, that's not true. There were like 3 videos that I made with this green screen. There was the first book review, the first video ever on this channel, which is the Lonesome Dove by Larry McMurtry book review, which is honestly pretty awful, but it's like, what do you expect for your first real YouTube video, if you want to think of it that way. And then there were like 2 philosophical videos, which honestly, this video will probably do as well as those. And get maybe like 50 views. Like if you go back and look at those videos now, they probably only have like 50 or 60 views, but they've been up for like 8 years now. And lately, you know, the views have been falling off, but I'm totally okay with that, because every single time that I set out to make one of these videos, I think to myself, I'm gonna go make trash. Because honestly, I think having that kind of a mindset is one of the keys to doing YouTube long term. Because, you know, I'll be honest with you, yeah, last year it was nice getting the pop of views from the, you know, momentum of the differential geometry reading streams. Lately I've kind of taken a dive off the deep end into the crackpot, grifter, conspiracy theory land. It's all good, because you know what, now that the views are going down, I'm like, awesome, this is an opportunity to experiment, have some creative liberty, switch things up. So I was like, you know what, I have this green screen in my cat son's bedroom, and he partly uses it as like a blanket. It's sort of like a TP style like blanket. Every day in the morning I quote unquote make my son's bed. You know, it's like not the best for his discipline. You know, I should be, you know, getting to do what I do, which is just when you wake up, make your bed first thing in the morning. But I'm just, you know, I'm trying to work with him. So I make his bed, but that means, you know, just straightening up this green screen. But I was like, you know what? I'm going to actually use it because I do all this fancy Final Cut Pro editing. Why not? So my goal is, the way I'm seated right now, hopefully I can just cut myself out from the green screen and then overlay myself onto the actual text. And so yeah, let's just get into it. If you're not familiar, we're reading Differential Geometry by Erwin Kreisig. I think there is a little bit that I do need to review, I guess. All right, so yeah, this is differential geometry. We're doing things involving curvature, involving topology. A lot of this involves surfaces, or in a more general mathematical sense, manifolds. And in order to define or work with these manifolds, we're often concerned with tangents, whether they're of just any given vector or maybe a differential vector. Maybe we're defining coordinate systems involving differential vectors on this manifold. But then the manifold, you know, being so general, maybe it's more than 3 dimensions to this manifold, and then it's like, that is embedded in a space greater than that. And so how do we generalize from our intuitions involving just 3 spatial coordinates? How do we translate that to those higher dimensions, if you will? That's part of the concern of differential geometry. So historically, along the way, I think it was Gauss who nailed it down as the first fundamental form, but we have this relation here. Maybe you've heard of differential forms. Maybe this is one of those forms. I'm not 100% sure. Whoops. I don't know what I'm doing. Okay, there we go. Okay, I can edit it out. It's fine. Okay. Anyways, as I was saying, okay, so we have the first fundamental form here, which is according to Gauss. The reason why I'm writing this out is because this is from like 50 sections ago in the book. And what I'm about to show is, okay, honestly, I did use AI. And let me back up a little bit. Okay, last video was the end of section 83. So that was minimal surfaces as translation surfaces with isotropic generators. And there were 3 theorems in the section, and at the end of the section we got to theorem 83.3, the third one of those theorems, and then we haven't had a problem at the end of the sections for a while, but then the problem is prove theorem 83.3. And the last video I cooked a steak. I was cooking the steak while I was reading the book out loud. And then by the time I got to the problem, the proof, I was like, dude, I'm going to do this in the next video. And the first differential geometry reading stream video, if you will, was the asking ChatGPT one of the problems from the very beginning of the book. It wasn't the preliminaries, but it was the first chapter of like real substance on the theory of surfaces. I asked ChatGPT the question, and then that was wrong, basically, or it was kind of, it was a slop of an answer. It wasn't a hallucination. I think I referred to it as that because, the terminology is ever evolving, as the English language will be, as long as there are speakers and users of the English language. It's always going to be a never finalized thing, right? Language and terminology. So got a slop answer that was like 42 episodes ago. But now I put in, just to find out, the question, which is just proving that theorem, which I'll get into in a second. And it used a different notation than what's in Differential Geometry by Erwin Kreisig, but I think is the more standard notation now, because this book was penned, actually written, not necessarily like published, disseminated, and then reprinted by Dover in 2008. It was like actually written in like the late 50s, basically. And so manifold theory and Riemannian geometry weren't as like specialized as sub-disciplines of differential geometry in general yet. And so someone actually commented on way, back a long time ago episode, that a criticism maybe of this book is that he seems like super doubled down, dedicated to using these really verbose, coordinate systems. Like you'll see here in a sec. Let me just, stop talking and do a little bit of the math here. So first fundamental form. This also reminds me of our good friend Scotty Chen, who maybe is still watching these videos. So, okay, I'm picking up again the story about the AI slop. Okay, so I asked ChatGPT the, prove theorem 83.3, which is for adjoint minimal surfaces S and S star, the asymptotic curves of S correspond to the lines of curvature of S star and vice versa. So the asymptotic curves of S star correspond to the lines of curvature of S, to spell it all out. So that assumes that you know what adjoint minimal surfaces are. So what's the difference between S and S star? Well, it's basically like it's a variation on complex conjugation where uh, you know they're offset by a complex angle of pi over 2 is what it comes down to, and they're minimal surfaces, which as we recall means that the mean curvature everywhere, or in this specific portion that we're interested in, the mean curvature is 0. And mean curvature is the arithmetic mean of the principal curvatures on the coordinate directions on these surfaces. So you recall what adjoint minimal surfaces are, and then you have to know what asymptotic curves are, and then what lines of curvature are. And these are concepts which are basically defined in terms of components of the first or second fundamental form, or like algebraic combinations of these components alongside like the differential unit coordinate vectors on this surface essentially. So in order to get to lines of curvature and asymptotic curves, you have to know the definitions of first and fundamental forms, which, so it's like, okay, that's maybe a suggestion of why they're called the fundamental forms. And I can get into this whole thing of like, Gauss and Riemann didn't have computers, and so, the style of math that they were doing isn't, maybe like statistics in order to basically serve the purposes of validating AI models, okay? So because we're in this particular period of time, mathematical research might, if you do like a random grab of it, there might be some stuff that's, to that effect. But back in Gauss's day, they were working on a lot of like quadratic, or so-called like the quartic. So it's not quadratic like, ax squared plus bx plus c equals, it's not like that. It's more like you could have like xy plus x squared plus y squared kind of stuff, right? The mathematicians of that time were, or at least Gauss was working on a lot of that kind of stuff. And so the first and second fundamental forms kind of came out of that. And so it's, this really heady kind of pure math realm, right? So, but nowadays, historically speaking, it feels like the first fundamental form is really not the one that's more important as far as like, ooh, what's a way to, because it's like, okay, we could have a metric. That's just kind of basically what the first fundamental form is, just kind of like a general metric, right? That obeys a triangle inequality. And, if you have two same points, the distance is 0, and, the symmetry, the distance between n and m is the same as the distance between m and n, sort of stuff. First fundamental form, that satisfies those 3 properties I just rattled off. So it's a metric. So it's kind of like not that big of a deal. But the second fundamental form is a little more to the core, if you will, as another way of putting it, to like the intrinsic geometry of these surfaces. Nevertheless, okay, so what I wrote out here is the first fundamental form. It's got this capital E coefficient, it's got this capital F coefficient, and this capital G coefficient. So if we rewrite, this was brought up earlier in the book, but capital E is equal to, it's basically the inner product of this vector x. So it's like, you have the surface, pick a curve on the surface, and now you're at a point on that curve on the surface. And so presumably this is a non-trivial situation. So you have some higher dimensionality going on here, but we're just going to limit it to ambient space, 3 dimensions. So your curve and your surface, you could define where you're at with 2 coordinates suffices. So being that it's like a vector valued situation here, you're at this point of interest. We've got in the du1 direction vector x1, okay? You do the inner product, which, let's just be tame. We're going to take the scalar product, just a normal dot product of x1 with itself. That's what this capital E is. So we can keep it real straightforward, and all these other coordinates are basically, the gist is the same. I got to make sure that I'm looking off to my notes to the side, because if I get anything wrong, like I just did now, it's embarrassing, because I always see that when I edit this, and really gets on my nerves. But maybe that's how I learn. Anyways, F, same thing. What did I just say? Scalar product, inner product. But now we're between x1, your first coordinate direction, on this surface, on this, maybe curve, you're walking along a path on this surface. X2 is the other direction. And typically, right, with the whole minimal surface is where the mean curvature is 0. Mean curvature is where we have the arithmetic mean of principal curvatures. Principal curvatures have principal directions. So these directions could be what we assign to du1. You could say maybe we've established that this is the maximum rate of ascent or descent at this point in this direction. We've figured that out. We're going to call that du1. And then we're going to say, okay, 90 degrees orthogonal to that, that's du2. Maybe that's what you do. Okay, now we take the values of x. We parameterized our surface. That's what x is in this scenario, okay? Scalar inner product, x1, x2, that's f, capital F here. Okay, moving on. Capital G. Same deal, but you guessed it. What's the only thing left? x2 with itself. You guessed it. Okay. This is probably already 30 minutes long, but it's all good. So now we're like, okay, this is pretty fundamental, bro. Same deal. Second fundamental form now, because, it's like I've got to be going somewhere with this huge rant, right? Okay, second fundamental form. Now we're going with lowercase e. Lowercase f, but we've still got, it's, for convenience, that we factor out 2. It's kind of like, I'm going to spell it out for you, because otherwise, in this definition right here for capital F, then if we wanted to get rid of that 2, then we would have to, put it in on the left hand side, multiplying on to the inner product of x1 and x2. And it's just like, okay, well, E and G, capital E and capital G are not defined that way. So it's like, you know what, we're just going to put it in the fundamental form. Anyways, du1, du2. All right, moving along. Last term, G du2, oops, squared. And if this is your first time watching, you're still watching, which is a Christmas miracle. It's statistically very unlikely, but this is a creative experiment, like I said. If you're still watching, but you don't know what's going on with, okay, well, we have these du1s, and the 1s are superscripts, du2, the 2's a superscript, but then that's squared, but then just right above here, capital E, capital F, capital G, we've got vector x. That's what I mean with the underlining the x, because it's really hard to bold with just, doing the stylus here. The indices are subscripts there for like the different coordinate directions. Okay, well, that goes into reviewing tensors and covariant versus contravariant indices. So contravariant is like the superscripts, covariant is the subscripts. And, go back and watch the tensor episodes. But the gist of it is covariant varies when you, in the same way, co-varying when you modify the underlying basis vectors. But contravariant vectors, which contravariant is kind of like the normal way you think about vectors, the length changes in the inverse way as when you change or perturb the underlying basis vectors. So like if you have just like a straight up vector that's length 1 and you make the basis vectors in half from what they used to be defined in terms of, then the length doubles, which is inverse of what you just did to the underlying basis vectors. So that's how we normally think of vectors. So that's the covariant, or I'm sorry, that's the contravariant way, right? See, maybe I'll edit it out, maybe I won't, but that's like one of the things I always get tripped up on, are like those kinds of distinctions where I make those kinds of mistakes on the fly when I'm just talking, and I feel like it just ruins my credibility right there, you know what I mean? Anyways, so back to the second fundamental form. This time, the second fundamental form is defined in terms of scalar products, inner products between the normal vector at the point on the surface, the point that you're interested in at this particular moment, particular reason, and this x sub 1, where basically this just means second partial derivative at least once in terms of the ith direction, once in the jth direction, which in this case it's symmetric, right? If you have just x1, x2, then x sub 1, 2 is the same as x sub 2, 1, which that's what lowercase f is in terms of. These should be vectors, right? I'm not going to spell out the definition of the normal vector right now. Whoops. Oh, goodness. Okay. Here we go. Okay. So it's kind of, you can see how, we have capital E, capital F, capital G. We have these inner products, same thing, lowercase e, lowercase f, lowercase g. So you kind of, see where maybe someone like Gauss would look at how things are cleanly, neatly written out. I mean, it's not very legible right now, but it's, the notation and all this, it's really clean, you could say. And it seems obvious, first fundamental form, second fundamental form. But it really comes down to then using these things, which example is what we're getting to now, asymptotic curves, lines of curvature. This goes back to, I want to say, like sections 40, sections 41, 42, somewhere in there. Recalling things like Moisnier's theorem, which is sort of like a near miss of what was to come in Riemannian curvature, maybe, and like it's like very near miss of contemporary Gaussian principal curvatures and principal directions and all that sort of stuff. But, all right, yeah, this was briefly mentioned in the book, right? Capital E, capital F, capital G. But then, alongside this, Erwin Kreisig was like, okay, we're going to call this G sub 1, 1. We're going to call this G sub 1, 2, which is the same as G sub 2, 1. And then we're going to call this G sub 2, 2. And so the first time he rolled it out, he did provide the alternative, so to speak, of capital E, capital F, capital G. But then, if you watch any of the subsequent episodes, he moved forward with G sub 1, 1, G sub 1, 2, G sub 2, 2. And then the discriminant of the first fundamental form would just be lowercase g. But then, similarly, for the second fundamental form, we also were introduced with like this lowercase e, lowercase f, lowercase g, and the Erwin Kreisig preferred alternative, if you will, was B. Okay, I'm going to have to erase part of this. All right, B sub 1, 1. Same kind of deal, you know what I mean? B sub 1, 1 going on here. B sub 1, 2 right here. And then this one, B sub 2, 2. Right? So first time, and wow, that's just like horribly illegible. 1, 1. He was like, all right, we could go one of two ways. Oop, we're going to go with G sub 1, 1 and B sub 1, 1. And then when I asked AI, okay, prove that if we've got adjoint minimal surfaces, asymptotic curves for one are the lines of curvature for the other, vice versa. Prove that mathematically. What I got was slop. It was a near miss because the definition of the adjoint minimal surface that it first provided was incorrect. At first, if you know, we defined our minimal surfaces in this case, we want to have complex valued vectors. So that's why the translation surfaces and isotropic generators were introduced, because then you could have a surface which you're just going to conveniently call Z, and then you could say that's equal to y of u1 plus x of u2, let's say. And u1, I mean, I made it a little bit obscure with that choice. We could say x of u1 plus y of u2. That's equal to your complex valued Z surface, right? And then it's just so convenient then that u1 is your real component and u2 is your complex imaginary component. So that's why you introduce formulating your minimal surface in this particular way, right? So the slop aspect was assuming that the adjoint minimal surface, you could just say, oh, we're going to do x of u1 plus I of y, or I times y u2. And then it proceeded with basically like a structurally correct proof, which is just like plug and chug by the definitions of asymptotic curves, lines of curvature, and just show by computation that they're equivalent. But it's like if you just put that straight up, you know, naively into this whatever, you know, chatbot you've got going on is, and you just don't vet the answer, then you look at the very tail end and you're like, oh, this is like a legit mathematical proof. No, it's not, okay? The correct answer involves where you have I times vector y in terms of u1 minus I times vector z in terms of u2. But this is where this huge, how long have I been going for? 30 minutes? What I did is then I followed it up and I was like, okay, reprint your output, but as a LaTeX file or LaTeX format, and I'm going to copy it and then I'm going to compile it as a PDF. But then I took that LaTeX that it gave me and then I edited it in order to come up with the correct answer. And then I added in other context and stuff like that. And that is how I came up with this right here. So hopefully I'm editing this together where it's like I'm floating in front of this document right here, okay? So great. Up at the top here, section 83 review. So this is all me. Theorem 83.1 was given to us by the intellect, the mind of none other than Sophus Lee. And someone once said that...
No. E8 as a group was only done much later. Neither Cartan nor Lee proved that there was an E8 group.
Oh.
If I'm not mistaken, Cartan discovered the E8 Lie algebra, which had been unknown to Lee.
Which is unknown to Lee.
Yes. Lee may what Lee did with Lie algebras, I don't know. But you could do it. Obviously there's he must maybe introduced the general concept of Lie algebras, although some special cases have been done before.
Yeah.
And proved some basic theorems about them. But he didn't classify them. I'm pretty certain. If I'm not mistaken, Cartan discovered the E8 Lie algebra, which had been unknown to Lee. I'm pretty certain.
So that's the Sophus Lee that we're talking about. This doesn't have to do anything with Lie algebras, but I just thought I would throw that out there. A surface is a minimal surface if and only if it can be represented as a translation surface whose generators are isotropic curves. Theorem 83.2, each pair of associated minimal surfaces can be mapped isometrically onto each other in such a way that at corresponding points the tangent planes to both surfaces are parallel. And then now what we're talking about today, Theorem 83.3 for adjoint minimal surfaces. Okay, I already read that. So as you may know already, every single problem that's in the 2008 Dover reprinting of Differential Geometry by Erwin Kreisig, which is not as conceptually complete as his lesser-known follow-up, Introduction to Differential Geometry and Riemannian Geometry, which kind of just like he wrote it and like published it at the University of Toronto or something like that, and then it just was never heard from again. And then 2008, they were like, nope, dig up from the slush pile. We're going to go back in the stacks. This guy's got potential. We're going to run with it. Here we are. Every single problem that's in this book, a solution is in the back. But the caveat is, as you can see here, it all fits on the screen all at once. It's a very short one. Some of those problems and solutions in the back of the book, they're very long and the text is smaller than the normal text. You know, it's very reminiscent of reading Infinite Jest by David Foster Wallace, and probably like the 5 people who are left watching the video right now have like, you know, one of you has clicked out because you're like, oh God, what a lit bro. But, you know, it's like reading Infinite Jest where there's those just voluminous endnotes. It's like no one has done endnotes to that degree. You know, no one's done endnotes all the way to the end like David Foster Wallace has, basically, you know what I mean, in Infinite Jest. And, you know, there's this back and forth between reading the main text of the book and those endnotes. And it's like, if you don't read those endnotes, you're missing out on critical parts of what's in the main text. You're being trolled, bro. But it's like kind of the whole preaching to the choir aspect of Infinite Jest, where it's like, oh, only the people who are so determined to go through the work to read that. Only they're the ones who are going to realize that, like, oh, society is going down because people don't have the attention span to read long books anymore, and blah, 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 and, you know, all that stuff. But it's like, you know, I'm reading Differential Geometry by Erwin Kreisig, and I'm like reading these, every single one of the solutions to the problems. You can go back to the videos. I've read them all back. And that's definitely part of understanding the subject matter, you know what I mean? But, like, you know, bringing it all back in, this is super terse. And there's this part right here where it's like, I wrote here, okay, asymptotic curves on a surface, that is to say, b sub alpha beta times du alpha du beta equals 0. I typed that part in there because in the actual solution in the back of the book here, okay, we have nothing. We have just in consequence of 39.4. So then you've got to go all the way back to the body of the text, and then we've got, you know, this part here, expression 1 here. So it's like if you just drop in, it's really hard to follow. So I kind of fleshed it all out here, but even then, it still is like very dense. So we came back over here. We've got the first and second fundamental forms. Hopefully you've written this down because, okay, now we're going to do a new one. Okay, so where's the pen? So asymptotic curves, I just wrote b sub alpha beta du alpha du beta equals 0. So you just read that and you're like, okay, that still does not mean anything to me. So let me spell this out. B sub alpha beta. I just said that Erwin Kreisig doubled down on referring to components of the second fundamental form by this whole B sub alpha beta thing. So when you have this written out, you're like, why don't we have B sub 1, 1, B sub 1, 2, B sub 2, 2? Well, this is written in what is known technically as Einstein's summation notation, which is basically christened after the renowned genius himself, Albert Einstein. Honestly, bro, I'm not saying Albert Einstein is overrated, but perhaps his genius was so bright that it's kind of, that has possibly led to theoretical physics kind of stagnating, because there's kind of this prejudice, right, of if someone were to come along and be like, I'm gonna pursue a PhD in theoretical physics, and the specialty is going to be gravitation and general relativity. That is literally the most pretentious thing ever said, possibly. That's like up there as one of the most pretentious sentences that you could come up with in the English language. But why? It's because if you say that, instantly you could be like, oh, well, who do you think you are, Albert Einstein? So it's like, there you go. The fact that, or, right, like calling something, oh, that's so complicated, what do you think this is, rocket science? It's like, okay, now doing something seriously related to rocket science sounds just like, I don't want to do this anymore because people are just going to like make fun of me because it's just like complicated. Not because maybe I'm not going to be able to do it, but just because like the optics of it to other people, it's just kind of like socially like repulsive to just like say that that's your goal or something like that. Back to this. Okay, so Einstein's summation notation, people were looking at this differential geometry stuff and they're like, God, this is just drag, having to write down these capital sigmas, these sums, and writing, okay, we're going to go from n equals 1 to n equals 2. But now we're going to go to 4 dimensions, and now we're going to just rewrite all the sigmas, and, you know, we have to change the upper bound on all these things every single time. You know, we're just like, we're going to get rid of that at this point. And then we're going to say, you know what? You know whose idea this was? Albert Einstein. Thanks, everybody. Einstein's summation notation. There you have it. So when you read this, you really have to know that, yeah, it does mean you multiply this out, or not multiply, you sum it out. You expand out the summation terms, but you just have to kind of like pick up on the context and know, oh, okay, this means we're going to have b sub 1, 1 du 1 squared, because alpha equals 1, beta equals 1 turns into that. But then you have to do alpha equals 1, beta equals 2, and then it's like, oh, remind yourself that alpha equals 1, beta equals 2 is symmetric with beta equals 1, alpha equals 2. Okay, so this turns out to be a differential equation, right? Because you've got these differentials here, and it's kind of like you want to figure out what the asymptotic curves are. You don't necessarily, it's not a given. You're trying to calculate them, but what does that mean, calculating them? Okay, you write out this definition for asymptotic curves. You get over the fact that anything that is named after Albert Einstein is just like, it's as cringy as wearing a t-shirt that says Big Bang Theory. Or like wearing the same t-shirt that character, what's his name, Sheldon on Big Bang Theory wears. If you wear that in public and you're like, oh, I'm a geek, I'm a nerd, I'm so witty, I'm so smart. Everybody at the grocery store, look at me, I'm going to carry around a math book at the grocery store. Okay, that is so cringe. That's how cringe I feel whenever I read that anything is named after Albert Einstein, basically. I'm sorry, I had to say it. Anyways, that's the Einstein summation notation definition of asymptotic curves. So that's the second fundamental form. Okay, now we're going to move on. Lines of curvature, because we're keeping the recap in this 40-minute, 50-minute, hour-long rant. We've got these adjoint minimal surfaces, S and S star. We have these two concepts related, kind of, asymptotic curves, lines of curvature. They're the same. We've just kind of basically defined asymptotic curves. Now we're going to do the same for lines of curvature. Basically, I'm just going to spell it out. All right, first term. Quantity lowercase f times capital G minus lowercase g times capital F closed quantity times du1 squared. So you can kind of see where this is going already. Next term. Quantity lowercase e times capital G minus 2 lowercase f capital F plus lowercase g times capital E closed quantity then times du1 du2. One more term. Very similar here. Quantity lowercase f capital E minus lowercase e capital F closed quantity then times du2 squared. And then this is all equal to 0. 0. So we're not intimidated by this here on my channel, Differential Geometry Gang. We are not intimidated by this kind of thing. Because if you look about it, we can just throw away all these quantities with capital, lowercase, E, F, and G. And now we can, it's kind of spelled out the whole, okay, this is not related to the asymptotic curves. But it's like, again, when you start getting into like going down the rabbit hole of deriving this, you can go back and watch the episode where it kind of does this basically. Do it for yourself with pen and paper. Is the first term is du1 squared. Second term du1 du2, and then the third term is du2 squared, right? But because we have orthogonal coordinates, we can basically get rid of this middle term here, the second term in this definition for the lines of curvature. It also simplifies things out when we're looking at the asymptotic curves as well. So that's kind of like a very high level view, but so getting back to this, I might as well just like read it verbatim now because, now it's just going to spell out in clear, rigorous. I mean, it's not like gold standard A plus, like, oh yeah, you got a PhD in mathematics. Not trying to be derogatory towards people who do have PhDs in general, or people who do have PhDs in mathematics. If you have a PhD and you're watching this video, leave a comment down below. I'd really like to know, because YouTube analytics doesn't show me the demographics of the education level of my audience. But when I look at my subscriber list of just people who have public that they show who they subscribe to, some people do have like doctor or like a common PhD in their name, interestingly enough. So I'd love to know what you specialize in, what you study, what your discipline is, what you did your PhD thesis on, or like if you're a grad student, I would love to hear you in the comments below. But so this is not at that level of your level. If I'm talking to you, if you're someone who out there, you have a PhD in mathematics or some STEM field, and you're like, dude, I could cook up some law tech right now that blows what you've got out of the water. You took AI slop, Anthony. You took the AI slop and you just basically corrected it and then dressed it up a little bit more. That's basically what this is, if I'm being totally honest with you. You could probably make something better. I believe you. Anyways, prove the theorem we've been talking about this whole time. Okay, so section 83 described translation surfaces with isotropic generators and introduced the family of associated minimal surfaces, which are isometric and have parallel tangent planes. One more thing. I went through the whole labor of talking about the difference in notations for coefficients of the first and second fundamental forms. And yes, we can maybe appreciate that the first fundamental form isn't as fundamental after all. The concept of a metric kind of does the job. Inner products, all that, we don't have to think about the concept of the first fundamental form all the time. Second fundamental form, maybe a little bit more juicy, as we just saw. It's a little more involved in things like the definitions of asymptotic curves and lines of curvature, right? But all this being said, Erwin Kreisig doubled down on calling these coefficients G sub 1, 1, B sub 1, 2, B sub 2, 2. But the AI slop, even though it's slop, is a little bit more aligned with the times, because it's maybe, statistically more likely that it picked up on the way most people have been talking about it. So that is the one, I'm not just trying to trash AI all the time, because if I'm being totally honest, yes, over time it is getting better. Can you just fill in the blanks of Riemann's Überhypothesen and get 12 pages of like awesomeness out? No. Me as a human, grind for like a month or something like that in my free time on the weekends. I'm not a PhD mathematician. Okay, you can look on my website, anthonymakesvideos.com/files, what I produced earlier this year. It's incomplete, honestly, because upon further review, there's more that could be done conceptually to make it complete from like a professional, rigorous mathematics point of view. I'm trying. Anyways, getting back to this, the advantage that I'm conceding to the AI slop is that it used lowercase e, lowercase f, lowercase g. But then at the very end here of this PDF, I just basically copied and then just like fleshed out the internal references within the book for using Kreisig's coordinate-heavy notation, G sub 1, 1, B sub 1, 1. So the purpose of all this is to maybe like contrast different proof styles, looking at like, filling in the blanks, filling in the gaps. Like, what does that mean? So like, yeah, you could undertake something massive relatively, like filling in the gaps of the habilitation thesis that kicked off Riemannian geometry. Or we could just get back to like this scheduled weekly homily advent calendar of reading differential geometry out loud. That's all I'm saying. And, just read the proof of one theorem, it's one problem, you've got hand holding in the back of the book, but then you can do your own, make it not just hand holding, right? It's not just hand holding anymore, right? It is if all you do is just read verbatim, just say the words of what the solution in the back of the book is. But then if you like take it, you flesh out what the internal references are into the previous sections of the book, then you ask AI, but then you have the wherewithal to realize that what it's giving you is wrong, okay? And then you could say, oh, you know what, I'm going to salvage this scenario by outputting this to LaTeX. And it's like, you don't have to be a superstar programmer. You don't have to be a Linux super user. You don't have to program only with the terminal. It's cool if you do. If you only use Vim, that's great. But you don't have to be at that level in order to just do LaTeX and take the AI slop and turn it into human silver, human bronze. Maybe it's not gold quite right away, straight away, but maybe you're getting somewhere with this. Okay. Theorem 83.3 connects the asymptotic curves, that is to say, curves where the normal curvature is 0, and lines of curvature, that is to say, curves tangent to principal directions, between adjoint surfaces, building on the isometric and parallel tangent plane properties from Theorem 83.2, which again, Theorem 83.2, each pair of associated minimal surfaces can be mapped isometrically onto each other in such a way that at corresponding points, the tangent planes to both surfaces are parallel. Continuing on, solving this requires understanding the second fundamental form and how the parameter alpha, which is in the definition or a formulation of these isotropic generators on translation surfaces. You have like a very weak, vague definition where it's just like z is equal to, z is your minimal surface, is equal to y of u1 plus, okay, it's equal to x of u1 plus y of u2. That's like a really weak formulation. You could gradually strengthen that formulation by adding in gradually more sophisticated or intentionally chosen coefficients of x and y. You could start with, scalar parameter t, move your way up to exponential functions with, complex values where you've got e to the I theta as a coefficient on x of u1 plus e to the negative I theta as a coefficient on y of u2, let's say. And you could have, you could slap that alpha in as a coefficient on theta. You can make it b theta or something like that. That's what we're basically referring to as this alpha here. So solving this requires understanding the second fundamental form and how the parameter alpha affects the surface's curvature properties. Now, after an hour, solution to problem 83.1, or the proof of Theorem 83.3. To prove Theorem 83.3, we need to show that the asymptotic curves of a minimal surface, S, parametrized with alpha equals 0, correspond to the lines of curvature of its adjoint surface, S star, parametrized with alpha equals pi over 2, and vice versa. So, first we're going to define, set up, in mathematical terms, the minimal surface S and the minimal surface S star, and we're going to set it up so that S star is adjoint to S. So, let the surface S be parametrized as the vector x in terms of coordinates u1 and u2, and we're going to set alpha equal to 0. This is equal to vector y in terms of u1 plus z, a vector as well, in terms of u2. Boy, I'm just realizing that I really set myself up for some confusion here with, anyways, and it's adjoint S star, which is parametrized as a vector x in terms of u2, and alpha is set equal to pi over 2, and then this is equal to e to the I pi over 2, then times the vector y in terms of u1, plus e to the negative I pi over 2, then times the vector z in terms of u2. And when you do a little bit of complex value evaluating here, you realize that this is just equal to I times vector y in terms of u1, then minus I times vector z in terms of u2. Where, with all of this being said, y and z are coordinate functions in addition to being vectors. That is to say, their real and imaginary parts satisfy the relations where we have partial u partial x is equal to partial v partial y, and partial u partial y is equal to negative partial v partial x, which is just the same as saying that the Cauchy-Riemann equations, that's what I just said, are satisfied in some complex analytical sense. And their derivatives of these y and z conjugate functions, getting back to that, the derivatives of these y and z conjugate functions satisfy the isotropic condition where the scalar product of y prime with y prime is equal to 0, and the scalar product of z prime with z prime is also equal to 0. Step 2, the first fundamental form. So for S, x sub 1 is equal to y prime of u1 and x sub 2 is equal to z prime of u2. And then we have our coefficients of the first fundamental form are then capital E equals the scalar product of x1 with itself, which is also then, as per the line above, the scalar product of y prime with itself, and this is equal to 0. Similarly, we have capital G is equal to the scalar product of x2 with itself, which is equal to the scalar product of z prime with itself, which is then equal to 0. And then we have that capital F is equal to the scalar product of x1 with x2, which is then equal to the scalar product of y prime with z prime, where again, y and z are these conjugate functions which we're parametrizing both S and S star in terms of. Thus, the first fundamental form for S is ds squared equals 2 times capital F, then times du1 du2. Similarly, for S star, we have x1 star is equal to e to the I pi over 2, then times y prime in terms of u1, which is equal to I times y prime in terms of u1. And similarly, we have that x2 star is equal to e to the negative I pi over 2, then times z prime in terms of u2, which is simply equal to negative I times z prime in terms of u2. And then continuing on to calculate the coefficients of the first fundamental form for S star, we have that capital E star is equal to the scalar product of x sub 1 star with itself, which then per the line above is simply the scalar product of I times y prime, scalar product with itself, which then this calculates out to 0. Continuing on, capital G star, another coefficient of the first fundamental form. If we were Erwin Kreisig, right, this would be lowercase g sub 2, because then this is equal to the scalar product of x2 star with itself, which is equal to then, per the line above, like I just said. Similarly, for capital E star, we have the scalar product of negative I times z prime with itself, and this is equivalent to just the scalar product of z prime with itself, which is then equal to 0. And then finally, we have the last coefficient of the first fundamental form for the surface S star. We have capital F star is equal to the scalar product of x1 star with x2 star, which is equal to the scalar product of iy prime with negative I z prime, and then this calculates out to the scalar product of y prime with z prime, which is then actually just equivalent to what we had calculated above for the corresponding coefficient of the first fundamental form for the surface S. But now we're looking at the coefficient for S star, capital F star, it's just equal to capital F. So therefore, the first fundamental forms are equivalent, and this all just shows to confirm that the surfaces S and S star are isometric. Step 3, And foreshadowing, we have 5 total steps here, and then we're still probably going to read over the proof from the back of the book. So again, it's a straight calculation proof. We're going to calculate the coefficients for the second fundamental form. Second fundamental form is Roman numeral 2 equals lowercase e, then times du1 squared, plus 2 times lowercase f, then times du1 du2, plus lowercase g times du2 squared, where lowercase e is equal to the scalar product of x sub 1, 1 with n, where n is the unit vector normal. It's the unit normal vector. I said that weird. Okay, anyways, we have lowercase f equals the scalar product of x sub 1, 2 with the unit normal vector. Same throughout all these coefficients. Then we have lowercase g is equal to the scalar product of x sub 2, 2 with the unit normal vector. And like I keep saying, n is the unit normal vector. For s, we have x sub 1, 1 equals y double prime in terms of u1. We have that x sub 1, 2 is equal to 0, and we have that x sub 2, 2 is equal to z double prime in terms of u2. From the proof of theorem 83.1, go watch the last video. X sub 1, 2 equals 0 implies that lowercase f equals, or which is equal to, rather, the scalar product of x sub 1, 2 with the unit normal vector. This is equal to 0. Thus, this is reiterating the definition of the unit normal. The normal is n equals a fraction with the numerator of x sub 1 cross product with x sub 2. It's Cartesian cross product. And then we have a denominator of the magnitude of the cross product of x sub 1 with x sub 2. This, in our particular situation, is equal to a fraction with the numerator of y prime cross z prime over a denominator which is the magnitude of the cross product of y prime with z prime. Thus, again, we're calculating the coefficients for the second fundamental form for the first surface, S, first surface, if you will. Thus, lowercase e is equal to the scalar product of y double prime with the unit normal, n. Continuing on, lowercase f is equal to 0, and lowercase g is equal to the scalar product of z double prime with the unit normal. Similarly, for s star, we're going to compute the coefficients of the second fundamental form. We have that x sub 1, 1 star, which is equal to partial x1 star, partial u1. This is also equal to partial u1 of essentially I times y prime of u1. This amounts to I times y double prime in terms of u1. And so that's x sub 1, 1 star. Continuing on, we can compute x sub 1, 2 star, which is just 0. And then we can compute x sub 2, 2 star, which is equal to partial x2 star, partial u2, which is equal to the partial derivative in terms of u2 of negative I then times z prime in terms of u2. So in this case, okay, spelling it out for you, negative I is just going to be a scalar, so then you take the derivative in terms of u2 of z prime of u2, and this just amounts to negative I then times z double prime in terms of u2. And we're then going to compute the unit normal vector, which is n star equals a fraction with the numerator of the cross product of iy prime with negative iz prime. And then the denominator is just the magnitude of the cross product of iy prime with negative iz prime. This then, after you do the complex arithmetic, equals a fraction with the numerator of y prime cross z prime over a denominator of the magnitude of y prime cross z prime. And this just computes out to be the same unit normal vector as what we had for the surface S. That is to say, the unit normal vector for S star is the same as the unit normal vector for S. Thus, lowercase e star equals the scalar product of I y double prime with n star, which is then equal to the scalar product of I y double prime with n, which is just equal to I times lowercase e, what we had calculated for S. Similarly, lowercase f star is equal to 0, and lowercase g star computes as the scalar product of negative z double prime with the unit normal, which is equal to just the scalar product of z double prime with the unit normal, but then times negative 1. But then that's just equal to negative I times lowercase g, where lowercase g is the coefficient of the second fundamental form as calculated for the surface S. We've just looked at how that's related to what we're computing for S star. So now that we've computed the components of the first and second fundamental forms for S and S star, defining that S star is an adjoint surface to S, and these are both minimal surfaces. Now, and the minimal surface aspect came into how we were able to say, okay, lowercase f is equal to 0, lowercase f star is equal to 0. It was from the proof of 83.1. What is 83.1? Sophus Lee. Surface is a minimal surface if and only if it can be represented as a translation surface whose generators are isotropic curves. Continuing on, step 4, we're almost there. Asymptotic curves, these satisfy a second fundamental form equals lowercase e times du1 squared plus 2 times lowercase f times du1 du2 plus lowercase g times du2 squared equals 0. What did I just say over here? B sub alpha beta times du alpha times du beta equals 0. In Einstein summation notation, once you're done cringing, that's basically what we just said here, right? It's just the different notations. Lowercase e, lowercase f, lowercase g. All right, lowercase b sub alpha beta, Einstein summation notation. Moving on, for S, since lowercase f equals 0, we have lowercase e times du1 squared plus lowercase g times du2 squared equals 0. We're going to do a little bit of algebraic arithmetic rearranging. We have e over g then times the square of du1 du2. This is then equal on the right-hand side to negative 1. Move e over g to the right-hand side. What do you get? We have the square of du1 du2 is equal to negative g over e. This defines the asymptotic directions, typically along where we have that u1 is equal to a constant or u2 is equal to a constant, since minimal surfaces often have asymptotic curves along parameter lines. Similarly, for S star, we have that lowercase f star is equal to 0, so lowercase e star times du1 squared plus lowercase g star times du2 squared is equal to I times lowercase e then times du1 squared minus I times lowercase g then times du2 squared is equal to 0. Algebraically resolve all of this and you have the square of du1 du2 is equal to g over e, where these are both lower cases, okay? Because now we're going to switch things up to lines of curvature and we're going to introduce lowercase and uppercase e, f, and g. Okay, these lines of curvature are curves where the direction along du1 and du2 aligns with the principal directions. For the surface S, since capital E equals capital G equals 0 and lowercase f equals 0, the lines of curvature are determined by capital F then times the quantity lowercase g then times du2 squared minus lowercase e then times du1 squared closed quantity equals 0. This implies that the square of du1 du2 is equal to lowercase g over lowercase e. Similarly, for S star, we have that capital F star then times the quantity lowercase g star times du2 squared minus lowercase e star then times du1 squared closed quantity equals 0. We're setting it up based upon the definition of lines of curvature. When I mean the definition, we derive this right here. So this just boils down the lines of curvature based upon the definition, if you will. We get the square of du1 du2 is equal to negative lowercase g over lowercase e. So to bring it all in, the final step, correspondence between what we've just laid out for these adjoint minimal surfaces S and S star. Compare what we have. The asymptotic curves of S, we have the square of du1, du2 is equal to negative lowercase g over lowercase e. And the lines of curvature we're expecting to match, but what do we have for S star? We have the square of du1, du2 is equal to lowercase g over lowercase e. Or excuse me, that's just atrocious. I'm going to do this right now live. I mean, we just... It's like, how can we allow this? How can we allow this to happen? All right, I just corrected the LaTeX PDF, hopefully in real time in front of everybody right now. You know, it's important that I rectify myself when these kinds of things come up. Anyways, this solution directly applies the concepts from section 83 by leveraging the section's framework of isotropic generators and the properties of associated minimal surfaces to investigate their geometric implications. So, yeah, of course. I mean, it's not like we're computing the coefficients of the first fundamental form for the purposes of, you know, asymptotic curves, lines of curvature only. No, we can also glean geometric properties like confirming isometry, that, you know, these two surfaces are isometric to each other, by going through and computing the coefficients of the first fundamental form, right? So you can appreciate that from the AI slop, at least it gets like the context of like explaining what the goal of the proof is and all that kind of stuff. I mean, it's not that complex of a proof. I keep saying it's just a straightforward calculation by definitions, a very basic proof technique, but you know, it brings in a lot of the understanding from the material, right? So now we're going to do the true solution from the back of the book. So to recap, we have the theorem here. I'm not going to read it again, but it's like I figured, hey, maybe after 4 pages it would help to have all of the theorem and the proof from the book all on 1 page. So the proof from the back of the book is as follows. We represent the minimal surface S in the form vector x parametrized in terms of u1 and u2 is equal to the vector y in terms of u1 plus the vector z in terms of u2. Then, according to x in terms of u1 and u2 and saying the parameter alpha equal to pi over 2, we have this is equal to complex I times, or imaginary I, rather, imaginary I, or the square root of negative 1, times vector y in terms of u1 minus I times vector z in terms of u2. The adjoint minimal surface S star can be represented in the form vector x star, or vector parametric representation x star in terms of u1 and u2 is equal to I times y in terms of u1 minus I times z in terms of u2. Since the component of the second fundamental form, b sub 1, 2, is equivalent to the scalar product of x sub 1, 2 with n. Those should be boldface vectors. Okay, anyway, so since the component of the second fundamental form, lowercase b sub 1, 2, is equivalent to the scalar product of x sub 1, 2 with the unit normal vector n, this is equal to 0. In consequence of the differential equation of the asymptotic curves on a surface, that is to say, b sub alpha times du alpha du beta equals 0, the asymptotic curves of S in this case are determined by the equation b sub 1, 1 then times du1 squared plus b sub 2, 2 then times du2 squared is equal to 0. Since we have the following components of the first fundamental form, namely g sub 1, 1, which is equal to, by definition, the scalar product of x sub 1 with itself, which in this particular case is equal to the scalar product of dy du1 with itself, this in turn turns out to be equal to 0. And similarly for the coefficient of the first fundamental form g sub 2, 2, which is equal to the scalar product of vector x sub 2, which is equal to the scalar product of the vector x sub 2 with itself, which in this particular instance is equal to the scalar product of dz du2 with itself, then turns out to be equal to 0. And the lines of curvature of S star are furthermore determined by the relationship lowercase g sub 1 2 star then times the quantity b sub 2 2 star then times du2 squared minus b sub 1 1 star then times du1 squared closed quantity equals 0. And this is derived from what we can refer to below. This is a determinant where the determinant is equal to 0, and when you compute out what this determinant represents, it turns out that what you obtain is what I wrote over here. You get the quantity lowercase f capital G minus lowercase g capital F closed quantity times du1 squared. That's what you get when you expand out this determinant. Okay, so column-wise, I'm going to read it out here, all the entries. It's just a 3 by 3 determinant here. So entry-wise, the 3 columns are, starting with the first column, we have du2 squared, and then we have g sub 1 1, and then we have b sub 1 1. And then in the second column, we have negative du1 du2, and then we have g sub 1 2, and then we have b sub 1 2. And then in the third column of this determinant, we finally have du1 squared, and then g sub 2 2, and then b sub 2 2. And then, like I said, this entire 3 by 3 determinant is equal to 0. So now we have the means to calculate the components of the second fundamental form for surface S star in terms of those for S and vice versa. So we have that b sub 1 1 star is equivalent to the scalar product of x sub 1 1 star with the unit normal vector, which then computes to be I times d squared y du1 squared scalar product with unit normal vector, which computes to be I times b sub 1 1. So in total, that's the relation b sub 1 1 star is equal to I times b sub 1 1. And so along the same lines, b sub 2 2 star, which is equivalent to the scalar product of x sub 2 2 star with the unit normal vector, is thus equal to, in this particular instance, negative I times d squared z du2 squared scalar product with the unit normal vector n, which computes out to be negative I times b sub 2 2. Again, in sum total, we've obtained a relationship between coefficients of the second fundamental form for these two surfaces. B sub 2 2 star is equal to negative I times b sub 2 2. And so by comparing expression 30, line 30 up here, and line 32, expression 32, we thus obtain the statement of the theorem. So that was an hour and a half. I'm looking at the time down there, and that's an hour and 32 minutes just crossed by. And so yeah, the last video we cooked a steak and we read section 83. We were exposed to 3 theorems, we proved 2. We rounded it off with a bit of a review as well, kind of on the fly, you know, reminiscing, or it's kind of like a tribute to how I did the cooking ground beef while reviewing differential geometry episode, right? Last one was steak, but we read from the book, going beyond that, and then now we had a little bit of an impromptu review because I went all over all that stuff about the first and second fundamental form. And we keep reiterating, you know, those themes, right? First and second fundamental form, keep reiterating principal curvatures, right? Principal directions, because in the theory of curves section of things, we define curvature as, okay, get to a point on your curve, find the second derivative, what's the length of that vector, and basically if you go in the direction of that curvature vector at that length and then just define the center of a radius of a circle there, that's where the notion of curvature comes from in the theory of curves. So then, like, okay, you go a little bit further forward in differential geometry by Erwin Kreisig. Sure, we go into surfaces, but we go into tensors, right? And then we really don't have any concrete notion of curvature. I kind of said this earlier. There was like Moisnier's theorem, okay, which is like a near miss, but then it really kind of came in with what's the classic differential geometry notion of curvature? It's Gaussian curvature. We can maybe agree on the definitions of principal directions, and we can steal from the theory of curves how we define curvatures and then have principal curvatures on surfaces. So that's how we can maybe go from curves to surfaces. We're trying to build up a notion of curvature on surfaces, maybe generalize surfaces from there. And so you get all these principal curvatures along principal directions, and you're at a fork in the road. You've got two choices. You can either multiply them all together or you can add them all together. But adding them all together isn't really a thing. Really what it is taking an average, right? I mean, yeah, you could like just straight up add them, but it's like, okay, but that's really the distinction. What it boils down to is you have all these principal curvatures, you've got a choice. You can multiply them all together or you can add them all together. Or you can just look at them, right? You can just have a table and have them all lined out, and then you could just say, you know, make a judgment value, whatever call you want, and say, you get to say what's important to you and what's not, what's relevant to your problem, what are you trying to look for, what are you interested in. You've got a dozen, throw away 10 of them. Great, that's what you're going to work with now. You could do that. Or you could multiply all of them together and then say, this is Gaussian curvature. We're going to put a handle on just this single number that we can calculate. And we're going to say the Gaussian curvature everywhere on this surface is positive. Gaussian curvature on a Euclidean plane everywhere, 0. Hyperbolic Gaussian curvature everywhere, negative. And then if you're Bernard Riemann, you'd be like, okay, this is how we're going to classify stuff. We're going to put all these things in tensors. Vectors aren't enough. We're going to put them all in tensors. And we're going to say, okay, well, that's it.